And if everybody can see that, then we're off to the races here. So this is, as I said, this is the whole subject that we're going to be looking into in some depth is known as structure-based molecular modeling, or in terms of drug design, then it's structure-based molecular design. And what it's all about is using knowledge of three-dimensional structures for biological molecules, usually proteins, but in some cases also some nucleic acids. And these are proteins which are associated with disease states or some other abnormal conditions. And the reason you want to look at the three-dimensional structures is so that you can see if you can understand the molecular details of normal and abnormal states. Because the thing about structural chemistry is that the way matter is put together determines its properties. And so there's a very direct sort of link between the structure of molecules and what the molecules do and how they interact with each other. So we'll get into some of that. And I hope you'll come out with a good understanding of what those details are like and how that's all related back to the structure of molecules. So you want to be able to understand the details that are associated with normal states and abnormal states, and the molecules that are involved, the proteins, enzymes, receptors, whatever, ligands for the receptors. And you want to then use that knowledge that you've gained about those details and try to find existing molecules or design new molecules which will disrupt that abnormal process. So if there's some enzyme involved in an abnormal condition, that maybe you can find something that's going to inhibit that enzyme, or with receptors, maybe you can find something that'll kick out the molecules that are causing the problem. I mean, a real great example is naloxone, and how naloxone binds even more strongly to opiate receptors than opiates do. So like morphine, heroin, and things like that. When you've got somebody who's overdosed and you administer naloxone, the naloxone binds so strongly to opiate receptors that it kicks out the opiates, and you can save somebody's life. And that's a very significant and sort of drastic example of a treatment of an abnormal process and disrupting an abnormal process, and how that's done. So this whole approach of structure-based molecular modeling and design is absolutely central to drug discovery research in academic settings and in commercial settings at pharmaceutical companies. Although there's a lot of interaction with academic groups as well. There's almost nothing that originates totally in a pharmaceutical company. Usually things are based on some academic research. So this is what we're going to be covering. And so as the slide says, for background, first we have to understand, for structural chemistry, we have to understand the three-dimensional structure of what are usually termed small organic molecules. So that would be the normal everyday molecules of things like, caffeine and those organic molecules. And then the distinction is the terminology is in when you work in molecular biology or structural biology or just anything that like protein studies and things like that, you refer to the sort of ordinary organic molecules as small molecules, and then you have the macromolecules, which are the proteins, nucleic acids, lipids, and so on. So that's the terminology here. The three-dimensional structure is really, it's the geometrical features, and it's very basic stuff like bond lengths, angles of bonds joining two atoms or associating three atoms, and so you've got two bonds and an angle between them, and this is how you describe the three-dimensional structure of molecules. With ordinary kinds of molecules, they're not so big that it becomes extremely complex to try to describe the geometrical features in that kind of detail, like bond lengths and angles and stuff like that. There's a greater kind of level of structure that we'll get into, and this is one of the things that it's important to understand. We'll talk about the common features of organic molecules, like we'll refer to functional groups like amides, hydroxyls, alkyls, phenols, and the sorts of properties that they sort of impart to the molecules. Then there are three-dimensional properties of molecules. So there are different spatial orientations for the same bonds. You could talk about stereoisomers then, the molecules that you can't superimpose with their own mirror images. Sometimes they're called optical isomers. That's a very big feature of biological chemistry. And then when you have relatively flexible molecules, then you talk about conformers, because there are different conformations, there are different arrangements in space of these functional groups. Then another very important subject is non-bonding molecular interactions, where you have how molecules are interacting with each other. So you have hydrogen bonds, you have ionic interactions, which are electrostatic interactions between charged parts of molecules. You have what are usually termed nonpolar interactions, which are interactions between like neutral groups on molecules. So they're commonly referred to as steric, van der Waals type interactions, hydrophobic interactions, and that's something that we'll get into all of that. And then that leads to amino acids as a particularly important class of molecules. So with all of the background information about the 3D properties and different functional groups and that kind of stuff that goes before, and then how all these groups interact with one another, we can start talking about amino acids and the fact that they are the subunits or the monomers or the residues that make up protein chains. And those are linked by a specific kind of bond, which is known as an amide bond or a peptide bond. Amino acids all share a common framework, and the thing that differentiates one amino acid from another is what functional groups are. That's the variable in the common framework, and we'll get into all of that. And then we'll talk about the visualization of three-dimensional structures, which is where you get into molecular modeling and software. And we'll look at a couple of different software packages that allow you to visualize molecules in 3 dimensions. And it's from my standpoint, it's fun to work with with that kind of software, and it's fun to be able to manipulate molecules in 3 dimensions on the screen, and that gives you a lot of insight. And then we'll of course, there are some common file formats for the structural files of their Cartesian coordinates generally, or you can specify molecules and their structures in terms of bond lengths and bond angles. But it's generally, you start with a file that has the Cartesian XYZ coordinates for each atom. And that's what you're looking at. That's what your software looks at. Then, with all of that background out of the way, what we do is then we start looking at the elements of protein structure and protein composition. There are 22, or depending on who's counting, 22 or 24. It's a set of distinct amino acids, which are the monomers from which the proteins are built. So proteins are polymers, but they're heteropolymers because the subunits are all different, but they're all, they're all put together the same way. The amino acids, we use the terminology of residue for the monomer units of proteins. And the amino acid residues, they're all linked by peptide bonds, and there's a linear sequence. So this is one way you start describing some very complex molecules. A lot of proteins have hundreds of amino acid residues. So you have to have ways to describe the protein in some logical way. And because proteins are linear polymers, there's a linear sequence. So what you do is you list the amino acid residues that are the components of a given protein. Generally, we use 1-letter symbols for the amino acids, and we'll get into those. And so there's a set of 22 or 24 1-letter symbols, and you can just specify a protein's composition by listing those symbols in the order in which they occur. And you generally go from left to right. So from the N, terminal end, to the C terminal end of the protein, left to right. There's a greater degree of structure in proteins, and sometimes and often, actually, not just sometimes, but often, proteins are made up of distinct subunits that are called chains. So you might have a protein that's made up of 3 or 4 chains of protein. Well, each chain is a separate protein which interacts with the other chains, and the interactions are the hydrogen bonds and electrostatic interactions and other interactions that we'll talk about before we get to the protein structures. And there are specific families of proteins that have these chain structures in common. And I think we'll be talking about a few of those, but that's in a couple of weeks from now. 3D properties, 3-dimensional properties. So within the chains, there are interactions among the side chains, the amino acid residues, and those create 3-dimensional forms. So the protein isn't just like a chain of beads, let's say, which is just a straight chain. There are some distinctive ways that these chains interact with one another to form 3-dimensional structures. And so one type of structure that is characteristic of proteins. The most distinctive kind of protein 3-dimensional property is the alpha helix. And that was first described by Linus Pauling, who actually was a big hero of mine in college. He was a real genius when it came to structural chemistry. And he first worked out the geometry of an alpha helix. He first described that, and that was published in 1951. And he described how the alpha helix is formed by hydrogen bonds between the residues along the chain. So instead of just having like a straight necklace of, let's say, pearls or something like that, you actually have a spiral that's held together by hydrogen bonds mostly. And so one interesting question is that we're not just dreaming all this stuff up. Protein structure data, there are experimental methodologies that will give you protein structures. And the experiments right now, the types of experiments that are done, in the past and now, there's X-ray diffraction, in which you're bouncing X-rays off of the atoms, and then watching the pattern that the X-rays make when they go through a protein molecule, and actually any molecule. You get X-ray structures for small molecules too, but for protein structures, there's a lot of data that comes from X-ray diffraction. Nuclear magnetic resonance, NMR, has been used and is being used to determine protein structures. And just recently, electron microscopy. There's three-dimensional electron microscopy, which is being used to determine structures of macromolecules like proteins and the nucleic acids and so on, RNAs. There is a central repository by pretty much consensus. So this is it's a consensual central repository where people who are publishing a structure send it to the RCSB PDB, and the PDB stands for Protein Data Bank. RCSB, they've changed what that stands for. It used to be based in Rutgers University, is where the R came from originally, but we'll get into some of the name changes and so on. And just as of last year, oddly enough, like a year ago today, or no, it's not the 23rd yet. But anyways, close enough. A year ago, there were over 145,000 structures available in the Protein Data Bank. So this is where you go. There's a website, and we'll get into all of that. And then how do you visualize 3D protein structures? Because we'll be looking at first a couple of software packages that are geared more towards looking at small molecules like organic molecules. But then when you're trying to display thousands of atoms at the same time, there are other software packages that have the capabilities built into them to show you alpha helical structures and things like that. So, you obviously you can't start looking at the atomic detail of protein structures unless you really zoom out first and get a good overall picture of the overall shape of the protein, and then try to zoom in on the areas that you're interested in. So we'll look at some of the software that's available. You'll use some of it, I hope, depending on it may be more or less easy to install these software packages, which are available for free on Windows systems, it could be a little bit more of a problem to install them on Macs. So, and I'm assuming that that's what people are using mostly, is Windows and Macs, generally laptops, I would guess. And then there are some structured file formats that have all the Cartesian coordinates and stuff. No, but you're talking about thousands of atoms in a protein. So we'll get into that towards the end. Like, this is going to be like pretty much week 3, I think, is what we're looking at. And then we'll be looking at, it'll all culminate in working with protein structures. So what we'll end up doing is downloading these PDB files from the protein data bank. The software package that I like to use the most is called PyMol, and it's actually good for both small molecules and proteins. And it's quite good with 3-dimensional visualization. We'll talk about protein ligand interaction. We'll talk about binding pockets in proteins. Maybe these are things that you've already come across. I don't know. They tend to be, you tend not to see these things until quite a bit later, like in college. We'll see how you can prepare a protein model for computation. There's another software package from UCSF, which is called Chimera, and that's a very good software package. So you generally, when you have X-ray structures, they don't have hydrogens in them. So this software will add hydrogens. It'll come up with partial atomic charges for all of the atoms, and then you can write the model structure to a particular file format, which we'll get into. We'll then look at the properties of binding pockets with a program which I wrote called Mol2Map, and then there's an interface for PyMol, for the PyMol program, that I also wrote, and I find it useful to look at binding pockets and see what makes them tick. And then there's some the idea of docking software, where you look at a protein, you specify a binding pocket, and then you will search, the program will search a molecule database for compounds that have structural characteristics that would cause them to possibly fit well into a given binding pocket, and the terminology is dock into a given binding pocket. So you can think of that as sort of like parking into a parking space that might be tight, or it might be give you a little bit more room, but that's kind of the same sort of thing that this program is doing. So it'll be looking at, the analogy is, if there's a small parking space, then the program is going to look only at compact cars. If it's a bigger parking space, then it's going to look at, all cars, SUVs, whatever. And if it's a really big parking space, then it'll look at trucks and try to get those in there. So that's kind of what you're doing when you talk about docking. And there's one particular program called AutoDock Vina, which I think comes from Scripps Institute, which is really good and very user friendly, because some of the original programs are just not user friendly at all. I would think of them as being user hostile. But so that's what we'll be covering in the first 3 weeks. And then there's going to be more of a research phase, which is where we'll get into some of this, some of actually working with these programs, and then we will take a look at, this is something that we did last year, but it'll be updated a little bit. We'll look at COVID-19 and the SARS-CoV-2 virus, and some of the things that have gone into producing vaccines for it. There are some particular aspects of this virus that are interesting and actually make it vulnerable to the immune system. In particular, there's this spike protein, like when you see pictures, depicting the SARS-CoV-2 virus. It's a coronavirus, so it has these so-called crowns, and they're actually these little bumps that you see on the surface. That's called the spike protein. Each one of those bumps is a spike protein, and it's a fairly complex protein, but we'll get into that. And there are lots of, I guarantee you, since last year, since a year ago, there have been tons and tons of new structures determined for the spike protein and other components of the SARS-CoV-2 virus. So that's what we're going to kind of focus on, because that's been of particular interest, unfortunately, for the past year and a half almost. So that's where this will be headed. That's where it becomes more concrete. So let me go back to so I've stopped sharing my screen. Any questions so far? Because then the next thing is going to be to look at just ordinary, like, chemical structure at first. So not talking about proteins or anything, just chemical structure and what goes into it. Oh, I just looked at the chat, taking notes now. Would I recommend that? If you want. If I'm not mistaken, this is being recorded. So eventually you should be able to, the recording should be available, I think, if you want to go back and rehash anything. And also, email me if you have questions that come up in between sessions. And if something's not clear, I'll try to clarify it then. But I would certainly recommend it if you've got any questions. Go ahead and ask, and because, like I said, the next thing is going to be to go into the larger kind of PDB material that I sent, and so we'll start talking about structure, the idea of chemical structure. So that's where we begin. That's where the whole thing begins. Okay, so let me see if I've got that. Nope, that's the. All right, so I'll set up again screen sharing, and we'll start talking about chemical structure. So let me, if I can find my Zoom session again on the screen. There we are. So let's share screen again. Okay, and then I'll set this up also as a slideshow, because I think it's easier to see everything that way. And So structural chemistry. The thing that eventually attracted me to chemistry was that it's a fundamental um, physical science. It's the science of matter. You know, when you come right down to it, and certainly physics deals with matter as well, but matter more in terms of energy, and it's not really, unless classical physics, when you're talking about, you know, billiard balls and stuff like that, and friction and things like that, but that's like beginning physics. And um, physics at the research level is also dealing with like high particle physics. You're talking about mesons and quarks and all this other stuff, but to me that sort of escapes my grasp, you know, because chemistry is the structure of the matter that we see every day and that we're made of. And so, you know, it's just something that's a lot more tangible. And um, that's, I think, what attracted me to chemistry, because I always like to get down to or maybe I have to, in order to understand things, I sort of have to get down to the fundamentals. And to be able to have a really good understanding of, let's say, biology or something like that, I have to be able to understand all the way down to the molecular level, and then things start making sense to me. So that's kind of my the way my personality works. So maybe that's one of the reasons why I got attracted to chemistry as the science of matter. And structure is kind of what matter is all about. It's the idea of structure is just absolutely central in chemistry. And to me, again, going down to the fundamentals, it's kind of remarkable to me that this whole structural kind of organization of structure of matter starts with particles that, for our purposes, you know, in looking at things from a chemist's point of view or a biologist's point of view, everything is put together from structures that are structureless themselves. So it's protons, neutrons, and electrons, and that's everyday matter is made up of these particles and little bits and pieces that really don't really have, unless you're a physicist, they really don't have structure themselves. So again, in chemical terms, these are the basic building blocks of everything. So the particles also, you can't distinguish one, say, electron from another electron, or you can't distinguish one proton from another proton, or one neutron from another neutron. They're all, you know, practically identical as classes of particles. So it then is just, I think, to me, it's remarkable that you can put all of these little guys together, and they just give rise to just, you know, almost infinitely many different quantities or entities that you can identify as being different from others. So one molecule is different from another molecule, and it all starts with these kind of dimensionless little bits. So when you start putting electrons, protons, and neutrons together, that leads to the first level of chemical organization, and that's what we call atoms. We see that as atoms, and atoms are the fundamental building blocks of chemistry. Um, Every atom has a nucleus. The nucleus is made of protons and neutrons. So the nucleus has positive charge because of the protons in it, and it has a mass because of the protons and neutrons. Both particles have mass. And then that nucleus is surrounded by a cloud of electrons. And it helps maybe to see them in classical terms as kind of electrons that are whizzing around the nucleus. But certainly in quantum mechanics, the more correct picture is that it's a cloud. And again, in quantum mechanics, it's a cloud of probability of where the electrons are most likely to be found. But in any event, you're starting to get some kind of three-dimensional structure already, because an isolated atom is spherical. If it's not interacting with anything, then it's spherical. Most of the mass is in this tiny nucleus, and the surrounding electron cloud makes up almost all the volume. So it's almost like there's empty space between the electrons and the nuclei, but that's what matter is made up of. You can identify atoms primarily by the atomic number, which is defined strictly as the number of protons in the nucleus. So hydrogen has atomic number 1, because the nucleus is just made up of 1 proton. Carbon has an atomic number of 6, so there are 6 protons in the carbon nucleus. Oxygen has 8 protons in the carbon nucleus, and so on. That's the atomic number that you see in the periodic table. When atoms are neutral, if they don't have any electrical charge, then that number, the atomic number, is the same as the number of electrons. But you can have ions, so that the atomic number is not the same as the number of electrons in an ion. But in neutral atoms, yeah, it's the same. But strictly speaking, the atomic number is the number of protons that the nucleus has. And so the periodic table is what you see there is an arrangement of elements where you're going from left to right in increasing atomic number. Atoms have a mass, and the atomic mass is pretty much comes from the nuclei, because the electrons have a mass, but it's a very small mass compared to the mass of a proton or a neutron. There's orders of magnitude smaller. So most of the mass is in the nucleus. Protons and neutrons have just about the same mass, and we tend to use atomic mass units to talk about atoms. So AMU, atomic mass units. Protons and neutrons each have a mass of about 1 in atomic mass units. Most atoms are going to have equal numbers of protons and neutrons, but what you see is that the atomic masses are in the periodic table they're not exactly whole numbers. It's not just twice the atomic number in the periodic table. So as an example, the most common one is something like carbon, and there are isotopes of carbon, and isotopes differ from one another according to the number of neutrons that they have in the nucleus. So carbon-12 has 6 protons, 6 neutrons. That's the normal situation. Carbon-13 has an additional neutron, so it's got 7 neutrons and a total atomic mass of 13. And carbon-14, which you are most probably familiar with in terms of carbon-14 dating, um, has 8 neutrons, and that makes it unstable. So that's why it's a radioactive isotope of carbon. And it's got 8 neutrons in the nucleus. And so if you take all of those isotopes, and if you take their relative abundance, carbon-14 is fairly rare, carbon-13 is a little bit more common than that, and carbon-12 is the most prevalent isotope of carbon. Then if you average all of that up, you get an atomic mass of 12.0107 in the periodic table. So it's a weighted average of the isotopes that you find in nature. For the same reason, hydrogen also doesn't have an atomic mass of 1, because hydrogen has isotopes. The regular, most common form of hydrogen just has 1 proton in the nucleus, so it's and that's all there is. There's no neutron, just a proton. So it has an atomic mass of 1. Then you have deuterium, which is H2, and that has a mass of 2 because it has a proton and a neutron in the nucleus. And then there's also tritium, which is H3, which has an atomic mass of 3. So when you look in the periodic table and you do the averaging for the relative abundance of those isotopes, you'll find that hydrogen has an atomic mass of 1.001, something like that, for the same reason. They're isotopes. So for us, it's a side issue because it's not something that affects the atomic structures very much, and we don't really care that much about isotopes for our purposes. So now we've gone through the structure, the first level of structure, which is atoms. We don't run into isolated atoms very much because they're quite reactive. And most of the experience that we have with matter is matter in molecular form. So a molecule is the smallest recognizable unit of most types of matter. So water, is so abundant. The smallest thing that we would recognize as water is a water molecule. That's the smallest level of organization. So a molecule is generally for most types of matter, it's the first kind of entity that we can differentiate from other entities. So, water is different from, let's say, octane. They're both liquids under normal conditions, but octane is very different from water, and we can get that all the way down to a water molecule versus an octane molecule. Some of the, and actually not just some, but a lot of the inorganic matter that we run into, like mountains and cliffs and sand on beaches and stuff, it's in mineral form, and that's not really molecular form. Those are ionic crystals like salts and silicates, but we don't really, our emphasis is going to be on biological systems, so we really don't run into inorganic matter in the form of salts and silicates that much in biology. That's not a kind of structure that we're interested in. We're interested in molecules. So as I mentioned, the smallest unit of water is the water molecule, the H2O molecule. The smallest units of carbon dioxide and methane you can characterize as CO2 molecules and CH4 molecules, respectively. And the smallest unit of caffeine is the caffeine molecule, which has this formula. It's a chemical formula. So C8H10 and N4O2. So in terms of how do we describe molecules? Well, the way we represent molecules is that chemists have, over a couple of centuries, have developed a very, to me, it's still amazing how powerful this symbolic language is. And it's pretty simple. And it's very versatile. And it's all based on the idea that molecules are composed of atoms, and somehow those atoms are stuck together. Now, in what we see up here, like the caffeine molecule and the chemical formula, the simplest representation of a molecule is the chemical formula, but that only tells you composition. It doesn't tell you organization. So caffeine formula, the composition of that is 8 carbon atoms, 10 hydrogen atoms, 4 nitrogens, 2 oxygens, but there's no information there about how those atoms are put together in the molecule, how they're arranged. And of course, they're not arranged in alphabetical order. That's how we do the chemical formula. We segregate things. We don't just haphazardly say, you know, C4, H5, C4, H5 again. So this is a systematic way to deal with the chemical formulas. But again, it's just composition and doesn't tell you anything about organization.
Sorry.
Yeah.
It seems that the slide that you're on right now, or that I can see, is still on atoms and not on molecules. So I'm not sure why, but the share screen is I see atoms.
So what's the heading that you're
Structure and
seeing?
chemistry.
Just, oh, so it hasn't, Is everybody having that same experience?
Yeah.
Hmm. That's kind of weird. So did anything change just now?
No.
Wow, that's going to be a problem. Was everything okay in the first set of slides?
Yeah.
Well, maybe I'm going to stop sharing and then go back and try it again. Okay, let's go back to share screen. And let's try. Let's try that one. And let's see if anything changes now.
Yeah, we can see the change in it. It's good.
Okay, good. I don't know what was going on there, but we're ready to go to the next page almost. Okay, so let's hope this works from now on. So we're going to spend most of our time, because the chemical formula isn't really telling us anything about structure, where the next symbolic level is the structural formula, oddly enough. And it's really, to me, remarkable how powerful the structural formulas are, because they actually summarize a lot of reality with just a few scribbles, just a few lines and letters. So we're going to look at the concepts that go into those scribbles, those lines and letters. And did everybody see the page change?
Yes, I believe so.
Okay, good. I hope we're back on track then with this. So what kind of information do structural formulas have in them? Well, you know, we have to talk about electrons and bonds. So bonds between the the atoms in these molecules, and those bonds are they have to do with the way the electrons are arranged. Okay. I have a complaining cat here, so I just picked her up, and maybe she'll settle down a little bit. Can't mute the cat. There she goes. Okay, so the way electrons are organized in molecules is pretty definite. If we start looking at where are the electrons going to go in the H2O molecule? So the oxygen has 8 electrons, and each hydrogen contributes 1 electron in H2O. So there are 10 electrons total in an H2O molecule. But so you can ask, well, where are they? Where do they go? And the accurate way to describe that comes from quantum mechanics, and it's in terms of molecular orbitals. And if you molecular orbitals are just 3-dimensional plots of the probability functions that tell you where the electrons are supposed to be. But we're going to find that just drawing lines on a piece of paper or a whiteboard or whatever can tell you an awful lot and convey a lot of that same information that you would get from looking at, you know, a complicated set of molecular orbitals in a structure. And what we're gonna think of it in terms of electrons being localized in bonds. And what are bonds? Well, we think of molecules as being made up of atoms that are joined by chemical bonds. And there are essentially 3 kinds of bonds that we can talk about, and the electrons that are involved in those bonds. The simplest kind is a single bond. And what that involves is 2 electrons in a bond, and each atom contributes 1 electron to a single bond. And that's what joins the 2 atoms together. So in the symbolic kind of vocabulary, a single bond is going to be represented by just like a short line segment, like a dash. So for the simplest molecule, H2, hydrogen, we can do that as in the following way. You get hydrogen, 1 hydrogen sticking to the other hydrogen. Each hydrogen contributes 1 electron. So we have a pair of electrons in the space between the 2 hydrogen nuclei. And from that, we get this H, single bond H representation. So you can sort of get a feel for how much information is being conveyed just by these simple elements of symbolic language. A pair of electrons is in this bond, and the bond is the space between the 2 hydrogen nuclei. And that's, you know, that's reality. That's pretty much how it really works. And in like in quantum mechanics, you would find out what the probability distribution is for the electrons in the hydrogen molecule, and you know, it's essentially the same information. For H2O, for a water molecule, what you get is 1 hydrogen contributes an electron, another hydrogen contributes another electron, and the oxygen ponies up 2 of its own electrons to form these 2 single bonds. And so you have H single bond O single bond H. So the rule that each line represents a pair of electrons that are being shared between the two atomic nuclei, that already tells us something about structure, because following that rule, the structural formula for H2O has to be HOH like this and not HHO, because each hydrogen can only contribute one electron to the bonding scheme. So, you know, what's this is an odd kind of formulation for it, because what happens to the other electron of the oxygen? There's one left over. And also, this isn't going to work, because if you want to have a single bond between two hydrogens, then each one contributes an electron, but that's all they have. Each hydrogen just has one electron. So this hydrogen then has nothing to share with this oxygen, and that's just not going to work. But this way works fine. So, you know, that's a rule. Each of these dashes represents a pair of electrons, and that's what's joining the two atoms that are bonded by a single bond. Next type of bond is a double bond. And you find that two atoms, you'll often find them being joined by a bond in which each atom contributes two electrons. So we picture that with two short parallel lines, two dashes that are parallel. So if we go through this procedure with carbon dioxide, we start with the chemical formula, CO2, and then we look at the schemes that you can use to pair up these electrons. And so oxygen has two electrons that it can share. Carbon has, as it turns out, it's got four electrons that it can share, but it can share a pair of electrons with an oxygen. So you get this O double bond C. Carbon has another pair of electrons that it can share, and the other oxygen has two electrons that it can share. So now you've got two double bonds in the carbon dioxide molecule, and you write it like that. And again, if you follow the rules for electron sharing, and so that each line, each dash symbolizes one pair of electrons, then following those rules gives us some structural information, because it can't be done this way, because each oxygen can only share two electrons per double bond. So these two oxygens blow their supply of electrons just in forming that bond, and then you can't really have this because you're not really sharing. Then carbon is just putting its four available electrons into this double bond, and it's just not how it works. It's not going to work that way. You want to get equal sharing. So that's the way the rules work for this symbolic language. And then the third common kind of a bonding scheme is called a triple bond. And that's where you join two atoms with each atom contributing three electrons to a bond. So in terms of, again, you're using a line or a dash to represent a pair of electrons. So a triple bond is going to be a sharing scheme for 6 electrons. And a couple of very simple and familiar molecules that have triple bonds are nitrogen, N2. 80% of our atmosphere is this stuff, N2. And it's two nitrogens which are joined by a triple bond. And same deal. Each nitrogen can contribute 3 electrons. So you end up with a total of 6 electrons between the 2 nitrogen nuclei, and you represent it this way with three lines, and each line represents a pair of electrons. And then there's hydrogen cyanide, which has the carbon and the nitrogen sharing 3 electrons each. At one end, the carbon contributes 1 of its 4 available electrons to, and then the hydrogen contributes another 1. So that's a single bond, HC. And then the carbon has 3 electrons left over, and the nitrogen has 3 to share. So then you get a triple bond, you get 6 electrons or 3 pairs. And that's what hydrogen cyanide then looks like. And here it's common to save kind of complexity. It's simpler just to write an H next to the C and not write in the dash. That's a fairly common thing that people do. So the single bond is implied here. So that's electrons and bonds and the symbolic kind of language that's being built up here. And then we get to, I think probably you've seen some of this stuff before. If you've taken AP chemistry or something equivalent, they'll go into stuff like this. Normally, you really get hit with this kind of stuff in organic chemistry, but we are not worried about all the extra baggage that comes with organic chemistry that doesn't really have anything to do with structure. Like you have to memorize chemical reactions and, you know, organic syntheses and stuff like that. We're not concerned about those things. We're only concerned about the structural aspects. So I think this probably will take us to the end of today's session, I think. Let me see what's, well, okay. We'll see how far we can get in 10 minutes. But these are definitely going to be the last 2 slides that we'll talk about today, and we'll leave it. And it's a pretty good place to leave it until next time. Electrons and valence. So, you know, not to get too wonky about the definition of valence, because people there are a few different things that people mean when they say valence in terms of bonding. We don't want to get too complicated. We want to keep it simple. So for our purposes, and it's a perfectly good definition, the valence of a given atom in a molecule is just the number of atoms attached to that atom in a given context. So here, for example, we have methane, and the valence of the carbon here is 4 because it has 4 other atoms attached to it. It has just these 4 hydrogens. And each hydrogen here has a valence of 1, which is, you know, the typical thing for hydrogen. It's only got 1 other atom bonded to it. For H2O, the oxygen has a valence of 2 because it's attached to 2 other atoms. In carbon dioxide, the carbon has a valence of 2 because it's attached to 2 other atoms. And each oxygen has a valence of 1. So this idea is it's directly related to the set of electrons that each atom has for bonding, and those are termed valence electrons. So those are the term valence electrons means the number of electrons that a given atom has for forming bonds with other atoms. So carbon always has 4 valence electrons, despite the fact that the atomic number of carbon is 6, which means that it's got 6 electrons. 2 of those electrons are tucked away into what's called the core, and they're not generally not available for bonding, but it does have 4 electrons of its 6 that it's very, very happy to share with other atoms. And so the carbon atom, right, it always has 4 valence electrons, but how are these distributed in the different bonding situations that we've already talked about? So, I mean, see, this is where the confusion comes in between the valence of an atom and the valence electrons. Although maybe it's not that confusing. See, if carbon can be, oh no, sorry, the valence varies. That's what I was trying to get at. So the carbon here has a valence of 2, but in the methane molecule, it's got a valence of 4. And that depends on how many atoms are attached to it. But in both cases, the carbon has 4 valence electrons. And those are the electrons that it can share with other atoms. So they can be distributed different ways. And again, Linus Pauling came up with the notion of hybridization because he was looking at atomic orbitals, which are coming from quantum mechanics, but we're not going to get into the specifics of how they come about in quantum mechanics. I'll only say that they come about from solving the Schrödinger equation for the hydrogen atom. So the solutions to the Schrödinger equation are hydrogen orbitals, hydrogen-like orbitals. And from that, there's a whole set of atomic orbitals that people use to describe atoms and the bonding situations. And Linus Pauling came up with this scheme called hybridization, which uses combinations of these atomic orbitals to explain the valence numbers and the geometry, the spatial direction of the bonds that are formed by a given atom. So not to go into too much detail, but this is what you'll commonly see, and you would definitely get this in organic chemistry in college. But I think it's it's totally understandable without going into the other stuff that you would get in organic chemistry. These are concepts that kind of stand on their own. So there is a direct connection between the valence and the molecular geometry, and that's you could see that on the next slide, and we'll maybe we'll just go to that next slide and take a quick look after we talk about the notations here, and then we can pick it up again next time at that spot, because this is where you're starting to get the notion of 3-dimensional geometry. So in hybridization, commonly single bonds are formed from sp3 orbitals, and the way you get those is you take one s orbital and 3 p orbitals, and you add those up and you get 4 hybrid atomic orbitals. And as it turns out, those have a spatial orientation, and those are oriented towards the corners of a tetrahedron in 3 dimensions. So you can look at that right here. So if you take an s orbital, which is spherical, and then you take 3 p orbitals, which are in the x, y, and z directions, they're oriented. They're like little dumbbells, sort of. And you combine those, you get sp3 hybrid orbitals. And this is just the mathematics that Linus Pauling worked out. And they have a tetrahedral orientation to them. So you see that in molecules like methane and methanol, you get that tetrahedral orientation from sp3 orbitals. So, you know, we just looked at methane and methanol as examples of things that are composed of sp3 orbitals. sp2 orbitals means you take one s and two p orbitals. So we just go to the next thing here, and again, a spherical s orbital and then two of the same p orbitals, but now they're only oriented in the xy plane. So you get something that is trigonal planar. So it doesn't have the third dimension, it's just planar. And examples of that type of hybridization are in ethylene, and that's what you see in double bond molecules, right? So ethylene has these two sp2 ends, and formaldehyde is another sp2 type molecule. We go back, and then the triple bond type is the typical type is the sp orbital, which gives you two hybrid orbitals, and they're just linear. So you take the s spherical, you take one of the p orbitals, and you get the sp hybrid orbital, and that's a linear orientation. An example would be acetylene, which is composed of sp orbitals. It's got a triple bond here, and hydrogen cyanide also sp orbitals in here, and it's also linear. Those are linear molecules. Oh, I forgot to mention that the terminology that's used with these types of hybridizations. So sp3 is characteristic of alkyl carbons, which have the 4 valence electrons in each one of those orbitals, those sp3 orbitals. sp2, the characteristic is alkenyl. They're characteristic of alkene compounds. So more organic chemistry terminology, but like ethylene, propylene, the hydrocarbons are called alkenes, and they have sp2 hybridization in them. And then the sp type is the alkynyl carbon. So like acetylene is alkyne, it's an alkyne. And that's a whole class of organic compounds as well. And they have the triple bond, and the hybridization that goes with the triple bond is sp. So if we just take one more look at this. So the sp3 scheme, 3 dimensions, sp2 scheme, 2 dimensions, planar, and the sp scheme, which is just 1-dimensional, linear. And then where are we going to pick up? Okay, so we can stop here. And that'll do it for today, I think. So if you have any questions before we all escape.
Yeah.
Okay.
For the bonds, like, because you said they're in orbitals, right? So they're always like moving kind of in this cloud, right?
Well, strictly speaking, it's a cloud of probability.
Oh, so are they not moving, or do we just not know where they are?
We don't know where they are. We know where the probability is, so we know where to find the electrons. If we really wanted to have some experiment where we shot an X-ray or something into a molecule, that's the basis actually of X-ray diffraction. So the X-ray would bounce off of the probability density and would make a pattern. The X-rays would make a pattern.
Okay.
But until we do that, that's sort of the essence of quantum mechanics. Until we make the observation, we don't know where they are. So it's just the orbitals. They're representatives of a cloud of probability.
I see. So we can't say that they're moving. We cannot say that the electrons are moving.
No, not in quantum mechanics.
Okay.
That's a classical picture of electrons as particles, whizzing around.
Hmm.
But in quantum mechanics, all we can talk about is the probabilities, probability density.
So when we have bonds, then those probabilities are centralized at those bonding areas.
Yeah.
Okay. All right.
Yep. And that's where we see, like when we do the experiment, when we do the observation, that's where we see the electrons localized
All right.
kind of
Cool.
between the nuclei.
Yeah. Okay, that makes sense. And then why does the bond stop at triple? Why don't we have a quad bond if we have carbon, which has like 4 valence electrons?
Well, there are some more exotic schemes, but they involve other elements in the periodic table. So we're going to be mostly concerned with the atoms that you would find, the elements that you would find in proteins. So, you're going to find carbons, hydrogens, nitrogens, oxygens, sulfur.
Mhm.
And even sulfur is already capable of some more exotic kinds of schemes. But
I see.
especially when you're talking about metals, and organometallic complexes and things like that, there are some fairly exotic schemes where they're not really amenable to simple descriptions like a single, double, triple bond.
Mm, okay, that's interesting. All right. And then last thing, you mentioned that sp had like a triple bond. So does that mean that sp3 is related to a single bond and sp2 related to a double bond?
Yeah,
Okay. All right.
yeah,
Cool.
that's exactly how it works.
All right. Cool. That's it.
Okay. And any other questions? And of course, if anything occurs to you before Thursday, then you just email and I'll see if I can help out. But while it's still fresh in your minds, if you have any questions, let me know. And if not, then we'll finish up.
So I just had a quick question. So hybridization is relevant to molecular geometry solely because it implicates its general shape of the atom, right?
Yeah, that's the first place where that's the first kind of idea where you start seeing um, uh, three-dimensional structure, like with the sp3 hybrid orbitals. So they're oriented in a tetrahedral way. So it's definitely a three-dimensional array of orbitals. sp2 is planar, but still, you're getting some structure out of that. And sp is the kind of the simplest thing, but it's packing a whole bunch of electrons between two atoms, like 6 electrons, but it comes out as a linear arrangement. But one of the things that I want to impress upon you is the how much information ends up in these lines that we draw structural formulas with. There's a lot of information there, and some of it actually corresponds to reality. We'll see that when we get into the more complicated kinds of molecules like benzene, rings, cyclical structures. But that's like next time. Okay. All right. So if everybody's good, we will finish up today. So I'm gonna go ahead and hit end, and uh, this was enjoyable. So I don't, good questions, and we'll see you next time. Maybe you'll have more questions before we start next time.
Thank you.
Thank you.
Mhm.
Yeah.
Thank you.
Thank you.
Thank you.
Bye-bye.
Where can we find the recording?
I don't know. I'm gonna have to talk to the powers that be and find out where they're gonna be putting these recordings.
Okay. All right. Thank you.
All right, thank you.